CORDIC stands for Coordinate Rotation Digital Computer. Back in 1959, an article was published by the Institute of Radio Engineers Incorporated and written by Jack Volder. Volder took a principle of geometry and created an iterative formula that can be implemented with digital logic to make complex calculations such as sine, cosine, hyperbolic, logarithmic, and various other calculations very quickly and accurately. In Jack's day, the CORDIC algorithm was used to replace the analog computers in the B-58 bombers. In 1979, Texas Instruments made the TI-35 calculator, which used the CORDIC algorithm to compute various trigonometric, hyperbolic, linear, and logarithmic functions. Today, the formula has been expanded and has many digital applications, including math coprocessors, radar signal processors, robotics, and software-defined radios. So where did he start? Let's take a look at what's involved. In this diagram, we see two vectors of the same magnitude. The second one is obtained by rotating the first one by an angle we'll call phi. When we rotate the first one located at x sub 0 and y sub 0, we get new coordinates of x sub n and y sub n. So how do we calculate x sub n and y sub n based on the input vector and the rotation angle phi? The new x sub n and y sub n are x sub n equals x sub 0 cosine of phi minus y sub 0 sine of phi, and y sub n equals y sub 0 cosine of phi plus x sub 0 sine of phi. Well, that's straightforward, but look at all the multiplications and the sine and cosine functions we'd have to compute to get the new coordinates. Wouldn't it be nice to be able to create some fast sine and cosine functions in hardware? Well, that's where we're heading in all this, but we have to discover how Volder did it. He produced these equations using additions, subtractions, and shift registers in a unique way. That's the goal in this presentation, to create the sine and cosine functions without multiplications or some sort of trigonometric type calculation. First, let's slightly change and rewrite the equations as x sub n equals cosine of phi times the quantity x sub 0 minus y sub 0 times the tangent of phi, and y sub n equals cosine of phi times the quantity y sub 0 plus x sub 0 times the tangent of phi. Well, that's nice, you're thinking, but there's still trigonometric calculations and multiplications involved. That's going to be slow in hardware or software. So far, nothing is simplified, but here's where the fun begins. Assume we only allow values of tangent of phi to be numbers of plus or minus 2 to the minus I, where I ranges from 0 to infinity. What will happen to the tangent of phi term? In this table are listed the values of I from 0 through 9, and the corresponding positive values for tangent of phi equals 2 to the minus I, and the angle in degrees represented by phi. In the table you can see tangent of phi values, in that middle column there, of 1, 1/2, 1/4, 1/8, etc. Notice that by multiplying by these tangent of phi numbers is the same as doing a shift right on the x and y variables. So yay! No multiplication for those terms. What do you think about that? You're probably thinking, kind of nice, but not very useful, as it can only do specific angles of 45, 26.565, 14.036, 7.125, etc. What good is that? And we still have a cosine multiply. Okay, fair enough, but we're not done yet. Let's look again at the last set of equations and the equivalent of cosine of phi, where we've restricted tangent of phi to specific angles of plus or minus 2 to the minus I. Cosine of phi is equal to 1 over the square root of 1 plus tangent of phi squared, which, because of the angle limitation we've imposed, is the same as 1 over the square root of 1 plus the quantity plus or minus 2 to the minus I squared. And we'll now call this k sub I. Then let's slightly change the last set of equations to reflect if we rotate by a positive angle or a negative angle of 2 to the minus I. I'll use the variable d sub I in the multiplication, whose value is plus 1 for positive angles and minus 1 for negative angles, assuming the maximum rotation in either direction is 45 degrees or less. Therefore, we now get x sub n is equal to k sub I times the quantity x sub 0 minus y sub 0 times d sub I times tangent of phi. And y sub n is equal to k sub I times the quantity y sub 0 plus x sub 0 times d sub I times tangent of phi, where d sub I is equal to plus or minus 1 depending on the direction of rotation. Cosine, square root, you're still thinking, well, what difference does this make? Now we have a square root function to compute. Right now, we are slowly building the pieces of a puzzle. Just make sure you understand each piece I'm showing you before we put all the pieces together and the picture just pops out at you. So, before we deal with k and the square root function, let's look at our problem of only using fixed angles of tangent of phi equal to plus or minus 2 to the minus I. Since we want to be able to compute any given rotation angle, and not just the one shown previously based on discrete values of plus or minus 2 to the minus I, an algorithm was created using these last two equations. Since we can make simple calculations using tangent of phi equals 2 to the minus I, then to get to a specific desired angle of rotation, we perform a series of successively smaller elementary rotations using tangent of phi equals 2 to the minus I, where I will be our rotation number. In this example, we start with the desired angle of rotation, which we'll call z sub I, which we'll say is 20 degrees. For each iteration, if z sub I is greater than 0, then we subtract the current iteration angle from z sub I. Otherwise, we add the current iteration angle to z sub I until hopefully we approach 0, or at least very, very close to 0. Once that happens, we have the new x sub n and y sub n that we originally wanted. Notice that in this example, at iteration 19, our error in degrees is quite small, only 0.000195 degrees. In general, we can use an iterative process to rotate by any angle by using these last equations for x sub n and y sub n. We'll use the index I to represent the current value and I plus 1 the next value in our iterative process. Notice that for k sub I, the sign of the angle is not important to k sub I, because cosine of positive phi is equal to the cosine of negative phi. Thus, at each stage in the iterative process, we'll always have the same k sub I value, whether we rotate in a positive or negative direction. We are only deciding which direction to rotate, not if we're going to rotate. It's important that k sub I for each iteration be a constant, because in a little while we want to remove this k sub I multiplication term from each iterative calculation. However, the sign of the angle is important to the tangent of phi term, which is determined by whether we rotate in a positive or negative direction. Therefore, we now have x sub I plus 1 equals k sub I times the quantity x sub I minus y sub I times d sub I times 2 to the minus I, and y sub I plus 1 equals k sub I times the quantity y sub I minus x sub I times d sub I times 2 to the minus I, and z sub I plus 1 equals z sub I minus d sub I times arctangent of 2 to the minus I, where I goes from 0 to n minus 1. D sub I is equal to minus 1 if angle z sub I is less than 0 and d sub I is plus 1 otherwise. Before proceeding about how to get rid of the k sub I term in the iterative process, Let's look at an interesting fact about the 2 to the minus I term and our x and y values. In hardware, the x and y values will be a certain fixed number of bits wide. Let's say they're 16 bits wide. What happens to the x sub I plus 1 and y sub I plus 1 calculations after the 16th iteration? In other words, what will happen to the terms y sub I times d sub I times 2 to the minus I, and also the x sub I times d sub I times 2 to the minus I, when I is greater than or equal to 16? Notice they both go to 0, and thus no more change occurs after the 16th iteration. This is very important for this iterative process, as you don't gain any more accuracy if you continue to iterate more times than the bit width of your variables. So, if you have x and y variables of 4 bits, and your quartic is based on this, then doing more than 4 iterations will be useless and wasting time and resources. With that in mind, we'll create an arctangent table whose bit width is at least as wide as the x and y variables, and a length that is at least as long as the number of iterations. Thus, to eliminate the arctangent calculation, a small lookup table is used, 1 entry for each iteration, corresponding to the arctangent of 2 to the minus I. Now we're getting somewhere. Just that pesky k sub I multiplication is left. Well, there's a way to get rid of that too during our iterative process. Now let's look at the k sub I term and notice that by removing the scale constant from the iterative equations would yield a shift and add type algorithm for vector rotation. The product of the k sub i's can be applied elsewhere or later in the system or treated as part of a system processing gain. That product approaches 0.6073 as the number of iterations goes to infinity. Therefore, without the k sub I terms, the rotation algorithm will have a gain, a sub n, that is approximately 1.647. The exact gain, without the k sub I terms, depends on the number of iterations as follows. A sub n is equal to the product of 1 over k sub I, as I goes from 0 to n minus 1, which is equal to the square root of the quantity 1 plus 2 to the minus 2i as I goes from 0 to n minus 1. Let's take a look. Here we have the first 3 k sub I constants in each iteration. K sub 0 is equal to 0.7071, k sub 1 is equal to 0.8944, k sub 2 equals 0.9412. Notice that k sub I is less than 1 and approaches 1 as we have infinite iterations. Since we have a limited number of iterations, the k sub I term can be pulled out of the equations and a final multiplication done at the end instead of during each iteration. Because the k sub I are always the same, remember that no matter what the angle we started with in this iterative process. By doing this, we get to our final set of iterative equations we'll use to make the quartic function. X sub I plus 1 is equal to x sub I minus y sub I times d sub I times 2 to the minus I, and y sub I plus 1 is equal to y sub I minus x sub I times d sub I times 2 to the minus I, and z sub I plus 1 equals z sub I minus d sub I times arctangent of 2 to the minus I. These can be calculated using addition, subtraction, and shifts. For the arctangent, a relatively small lookup table can be used. However, because we pulled out all the k sub I terms, the magnitude of each x sub I plus 1, y sub I plus 1 vector calculation was bigger than it should be by a factor of the square root of 1 plus 2 to the minus 2i. In other words, we rotated to the next angle OK, but the magnitude of the vector was a bit larger than it should be because the k sub I term, which is less than 1, is no longer there. Thus we wind up with a calculation for x sub n and y sub n with a system gain called a sub n, as discussed previously. Now that we have an algorithm which can be created in digital logic, what can we do with these equations? Not only does this algorithm compute a vector rotation, but by setting y sub I equal to 0 and x sub 0 equal to 1 over a sub n, we get a function that produces x sub n is equivalent to cosine of z sub 0, and y sub n is equivalent to sine of z sub 0. Did the puzzle just come together and the picture pop out? Nice! We've got a way to produce sine and cosine functions in digital hardware or even software. Not only can we use this method to get sine and cosine, but with a few twists we can produce other trigonometric functions like arc cosine, arc sine, logarithmic, hyperbolic, linear, and other functions too. Say adios to those long polynomial multiplication series to produce these functions. Get on the internet and start doing a search of quartic, and you'll find a whole lot more about them and what others are doing to make improvements. Maybe you too will find a new algorithm and help the engineering community. There's one more item that we skipped over while discussing this algorithm. These quartic equations are limited to rotation angles from minus pi over 2 to plus pi over 2 due to the use of 2 to the 0 for the tangent of the first iteration. For composite rotation angles outside of this range, an additional rotation is required, which is done before using the quartic algorithm. If the angle needs to be pre-rotated, we do the calculations as follows. Our new x sub 0 will be equal to minus d times y sub 0, and our new y sub 0 will be equal to d times x sub 0, and our new z sub 0 will be equal to z sub 0 minus d times pi over 2, where d is plus 1 if y is greater than or equal to 0, otherwise d is minus 1. There is no growth or gain for this rotation. In the second part of this presentation, we'll actually design the quartic function in Verilog and show some simulation results in ModelSim. Now let's look at an actual Verilog code implementation of this quartic algorithm. It can be written very concisely. This is a basic quartic function as described in part 1 of this presentation. Improvements could be made, such as rounding the outputs of each stage to reduce error and other things, but it's still quite accurate. After looking at the Verilog code, I'll run a simulation that will display sine and cosine outputs by feeding this quartic the proper inputs. In this slide and the next 6 slides, we'll cover all 148 lines of Verilog code that make up this quartic algorithm. First, notice line 12 contains inputs clock, angle, xn, yn, as well as outputs x out and y out. In part 1 of this presentation, the x sub 0 and y sub 0 would be represented by the xn and yn signals, and the x sub n and y sub n are represented by the x out and y out signals. In lines 18 to 24, the variables are declared as well as their size is specified. Also, these are signed variables, except for clock, which is just the system clock at which we want to run this code. Line 14 is a parameter definition that defines the size of the xn and yn signals as well as the x out and y out variables. However, you will notice that x out and y out are 1 bit wider. This is because the algorithm produces a system gain of approximately 1.647 due to the removal of the case of I terms we talked about previously. In this example, the size will be 16 bits wide. But since this is a parameter, it may be overridden with a different size wherever this module is instantiated in other Verilog code. Line 16 specifies that the number of stages or iterations will be equal to the bit width of the x and y variables, since anything more would be wasted resources and execution time. The angle has been declared as a 32-bit wide value, and in the next slide we'll see the table. 32 bits was chosen as the width so as to give enough resolution should the user wish to change the xy_sc parameter on line 14 to a larger value. If the value is over 30, then the width and length of the arctangent table will need to be updated appropriately. The unique thing about the angle is that no matter what size you may ultimately choose, its range covers the entire 0 to 2 pi range. By doing this, the upper 2 bits of the angle can be used to know which quadrant you're currently in. We'll look at this in more detail. Here we have the first part of the arctangent table, which is really a set of constants. Each constant is used at a particular stage and no others. Thus, arctangent table of 0 will be used only in the first iteration logic. Once again, angles are represented as scaled values. For example, arctangent of 0 is the value for the arctangent of 2 to the 0, which is 45 degrees. To create a 32-bit scaled value, I simply multiplied 2 raised to the 32 times 45 and divided by 360. The other arctangent entries are made in a similar manner. Here's the end of the table. Again, notice that if you have more than 30 iterations, the value will be 0, and thus you'll get nowhere in your z sub I rotation. As I mentioned, you can expand the width and depth of this information as needed. Next are the x, y, and z register declarations for all stages or iterations. In this case, each x sub I, y sub I will be 17 bits wide, and z sub I will be 32 bits wide. Notice that there are a set of registers for each stage instead of just a single set that gets reused for 16 iterations. This is known as pipelining. If we reuse the same set of registers for each iteration of the calculation, then the process would take 16 clock cycles before another calculation could be done. By pipelining the iterations, as you'll see later, we can effectively do a new calculation every clock cycle. The only drawback is that the output is delayed by 16 clocks, or n clocks, depending, of course, on the width of the x sub n and y n variables. This portion of the code determines if a pre-rotation of the inputs needs to be done and saves the values of xn, yn, and the angle in the x sub 0, y sub 0, z sub 0 registers. Lines 82 and 83 define a variable called quadrant, which is 2 bits wide and is equal to the upper 2 bits of the input angle. Remember, I told you this scaled angle value covers the entire 0 to 2 pi range, or 360 degree range. Thus, by looking at the upper 2 bits, we can determine which quadrant the initial rotation angle is in. The 2-bit value of 0, 0 means the rotation angle is in the 0 to pi over 2 quadrant, and thus no pre-rotation is necessary. Similarly, a 2-bit value of 1, 1 means that the rotation angle will be in the 0 to minus pi over 2 quadrant, and no pre-rotation is necessary. However, if the 2-bit value is 0, 1, then the rotation angle is in the pi over 2 to pi quadrant, and the inputs need pre-rotation as shown in lines 86 to 101. Similarly, if the 2-bit value is 1, 0, then a pre-rotation is also done in lines 103 to 108. Look closely at how pi over 2 is added or subtracted from the angle before saving it in the z sub 0 register. It's simply a matter of changing the upper 2 bits of the scaled angle value. Here is shown the entire code for all of the iterations or stages. Lines 118 and 138 are the generate and in-generate keywords, which basically means we're going to replicate logic. In this code, the logic is replicated 15 times for stages 1 through 15. To do this, a genvar variable I is used in conjunction with the for loop in line 119. The duplicated code is between the begin and end keywords of lines 120 and 137. Let's go through the logic. First, we have a 1-bit wide variable called z_sign. This too is replicated 15 times, one for each stage of the pipeline. Think of each stage as a block of code that is connected to the next stage in a certain manner. Next, variables x underscore shr and y underscore shr, or x shift right and y shift right, are declared for each stage in line 122. Lines 124 and 125 define how they are calculated. Notice they are assigned values, and the number of bits they are shifted right depends on what stage they are at. Line 128 calculates the sign of the current rotation angle, which is simply determined by the most significant bit of the angle because of how we've defined the scaled angle value. Finally, in lines 130 through 136 are the pipeline stages of the x, y, and z variables. In line 133, we see that the next value of x is determined by the calculation that follows. Notice it tests the sign of z sub I. If z sub I is 1, then the angle is negative, and the value of d sub I will be equal to minus 1. Notice it uses this to determine whether to add the y underscore SHR or subtract it according to the algorithm. Similarly, the next value of y is calculated, and finally the next value of z is calculated based on the current value of z and the sign of the angle, which determines whether we add or subtract the arctangent value from the table. Actually, the way the Verilog code is written, there is no table actually generated. It's just merely the appropriate constant is used in each stage of the pipeline. I use the term table because it's easier to understand when initially discussing this topic. The final lines of code merely assign the last stage of the pipeline's x and y values to the x out and y out signals. So that covers all of the Verilog code to make the coordinate. Next, we'll look at a simulation of the code generating a sine and cosine output. This simulation consists of three basic files: the coordinate.v, which we've been looking at in the rest of the presentation, a coordinate_test.v, which is the stimulus file for this simulation, and a sim.do simulation script to run this simulation. All of these files will be included with this video on my website at www.hdlexpress.com. Let's first look at this script here. Basically, all this does is invoke the simulator with some arguments and start with our top level module, which is coordinate_test. And it also has some signals set up in a waveform that you'll be able to see, and then just tells it to run it. Let's look first at the coordinate_test.v. This is a stimulus file, a behavioral model to simulate driving the input of our coordinate.v module. So in this module, I've declared a local parameter called sz for size equals 16, and I use that in these variable declarations xn and yn, and also x out and y out. Again, notice that my x out and y out is one bit larger than the xn and yn, and that's because of the gain, overall system gain of the coordinate. I've also declared a couple of local parameter variables called true and false, a local parameter called value, and I set it to an input of 32,000 divided by the system gain. I'm going to reduce it by a factor of system gain, so that during the sine and cosine outputs, we'll get an overall gain of 1. In other words, we'll get, if we put 32,000 in at the correct time, at sine or cosine at the proper time, we'll get about 32,000 out if everything works right. Then I've declared a register called I that I use, and then I have an initial block. The initial block is where everything begins in the simulation, and this initial block from here down to here, line 48, is the entire stimulus that I feed into the coordinate. You'll notice that I print out a statement. I set the beginning value of my 100 megahertz clock, because that's what I'm going to simulate running at. I set it to a logic level of 0. We'll look at the clock later on in this. I set the input angle to the coordinate to be 0. I set the xn to be value, which is 32,000 divided by the system gain. And I set yn to be equal to 0. By doing this, we're going to get an x out equal to 32,000 times the cosine of the angle, and y out equal to 32,000 times the sine of the angle. Then I just delay a little bit, and then I wait till the positive edge of my clock, and I set a signal called start equals true. And you'll see that in the simulation so that you can see where this particular line of code executes, just for a reference. Then I have a for loop that basically goes from angles 0 to 360 in increments of 1 degree. So we're not going to take a great degree of resolution here, just a 1 degree increment. And so at every positive edge of the 100 megahertz clock, I'm basically going to set the new angle value. And remember, I'm multiplying by 2 raised to the 32 power, that's what this effectively does, times my angle, I, and divided by 360. That will give me an angle that matches what I expect for angles to be in the quartic. And then I also print this out. And then when it's done with that, I just delay a little bit, print out the simulation is finished. Next, we have the instantiation of the quartic that we're going to be driving. Here we have its 100 megahertz clock input, the angle, the x and y in, the x and y out. So let's look at the next set of code here now. This is basically just a clock generation. So every half a clock it changes the polarity of the clock, and that generates my clock for this. So now let's go and run the actual simulation. Oh, looks like I did. I'll do it again. Do sim.do. And there you can see in my project the 2 files. So there it ran it. It runs pretty quick. It's a very simple test. And you'll notice there's the start signal that I talked about. The clock, I'll zoom in so you can see it better. The input angle, which is going to step in 1 degree increments every clock cycle. So we're changing the input every clock cycle because we've pipelined the architecture for the quartic. And then the xn, now remember it was 32,000 divided by the 1.647 system gains. That gives you this value here. And notice at the appropriate time, the x out for the angle is going to be right at 32,000. This error is very small. And here you can see that every clock cycle the values change. And we'll zoom in here. Then I'm going to show you something more interesting. So let's just zoom in right here at the beginning. So here you see our start signal. Now remember that due to the pipelining of this architecture and how long it takes to get the first result out, you notice from start all the way to where actually output starts changing is going to be our delay of 16 clocks basically. So, and that's what we see happening here. So now you could go through and you could collect all these values. You could maybe stick them in a spreadsheet, compare them with some calculations made in Excel or something like that. But one of the nice features of ModelSim is you can take the outputs, such as the X out and Y out, and you can change the format to analog and watch what happens. You don't see anything yet. I'll change the other one. Format, analog. Okay, now you'll see it's an analog type signal. So let's zoom so we can see the whole thing. And what do you know? We have sine and cosine functions. Now you might be looking at this and thinking, well, it looks kind of jagged. Well, yeah, there's 2 reasons for this. One is we only took 1 degree increments, and the other is the resolution of the screen itself. So the number of pixels on the screen from the high to the low, I think, is only about 72 pixels or something like that. Anyway, those are the 2 factors of why you're seeing the little jaggy edges. Now, if we zoom in, let's zoom in right here, just on a small area. And you can see that from here to here it looks flat. But there's several clocks, so we'll put our cursor here. Notice the value, 31,045. And it's still flat looking on the screen. But notice how the value has changed. So there is actually change in here in resolution that you don't see due to just the resolution of the screen. So anyway, hopefully you'll find this quartic fun and interesting, something to do, and maybe you can create other functions besides sine and cosine. Do a search on the internet, try things out, run a simulation, and if you can do another function, send it to me and I'd like to look at it. Thanks.